The James Webb Space Telescope, JWST, has made one of the most exciting discoveries in recent years. This discovery could change everything we thought we knew about the universe's beginnings, even offering clues about what might have happened before the Big Bang. This is a question that has puzzled scientists for decades. The Big Bang theory is the leading explanation for how the universe began. According to this theory, about 13.8 billion years ago, the universe started from a tiny, extremely hot and dense point, often called a singularity. From this point, it suddenly began to expand and cool, creating everything we see today, from the smallest atoms to the largest galaxies. One key reason scientists believe in the Big Bang is because of what is called Hubble's law. This law observes that galaxies farther away from us are moving away faster, suggesting the universe is still expanding. It's like a balloon being blown up, where dots on the balloon's surface move apart as it inflates. But even with all this, some questions remain. What actually caused the Big Bang? What was there before the Big Bang? Is the Big Bang really the beginning of everything? These questions are difficult because the Big Bang theory describes what happened after the universe began expanding, but doesn't fully explain what came before. Scientists use many tools to study the early universe. One of the most important is the cosmic microwave background radiation, CMB. This is a faint glow of light spread evenly across the entire sky. The CMB is like a snapshot of the universe when it was very young, only about 380,000 years old. Back then, the universe was filled with a hot, dense plasma where light could not travel freely. It was like trying to see through thick fog. But after about 380,000 years, the universe cooled enough for atoms to form. This made space transparent, allowing light to travel freely. This moment is known as recombination, and the CMB we observe today is the leftover light from that era. The temperature of the CMB is about 2.7 Kelvin, just above absolute zero, making it incredibly cold. But tiny variations in this temperature, only a few millionths of a degree, show us where matter was slightly denser or less dense. These small differences would later grow under gravity to form galaxies, stars, and planets. The early universe's composition, as revealed by the CMB and other measurements, matches the predictions from Big Bang nucleosynthesis. This is the process where the first simple elements, such as hydrogen, helium, lithium, and beryllium, were formed during the first few minutes after the Big Bang. Studying distant galaxies also helps us understand the universe's history. The oldest galaxies are seen at the farthest edges of the observable universe, meaning we see them as they were billions of years ago. Galaxies closer to us are younger and more evolved, showing us how the universe changes over time. But the Big Bang itself raises deep questions. Many scientists wonder if it truly was the beginning of time and space or just a transition from something earlier. Some theories suggest the universe could have existed in different forms before the Big Bang, or that it goes through endless cycles of birth and rebirth. One such idea is the Big Bounce, which suggests that the universe expands and contracts in a repeating cycle. Instead of a single beginning, the universe could have bounced from a previous collapse into our current expansion. Another proposal is the periodic egg scenario, where the universe repeatedly cycles through phases like a cosmic egg cracking and reforming. This suggests that time and space have no true beginning or end but repeat endlessly. From the world of advanced physics, the pre-Big Bang scenario comes from string theory, which tries to unify all forces and particles into one framework. This theory suggests that before the Big Bang, the universe existed in a different state governed by string-like objects in higher dimensions. The boundaryless proposal is another theory, saying the universe has no edges or boundaries in space or time. This means the Big Bang was not a sudden explosion but a smooth beginning where time itself came into existence. According to this proposal, the universe could have begun as a quantum fluctuation from nothing, a tiny, random blip in the quantum vacuum that created everything. Quantum mechanics describes this with wave functions, mathematical tools that represent all possible histories of the universe. These wave functions carry information about how the universe looks and behaves, including the distribution of matter and energy. They suggest that the universe's beginning is not a single point but a range of possible states with different outcomes. While these theories may seem strange or abstract, they show that scientists are actively searching for a deeper understanding of our cosmic origins. None of these ideas have been proven yet, but they help expand our imagination about the true nature of reality. One major goal of modern science is to explain how the universe truly began. The new discoveries from the JWST, such as the identification of a proto-galaxy cluster, give us fresh clues to work with. The universe is believed to have a hierarchical structure, meaning that smaller things came first and gradually combined into larger structures over billions of years. At the earliest stage, matter and energy were spread evenly throughout space, with tiny bumps called perturbations. These were tiny differences in density that eventually led to the formation of galaxies and clusters. These perturbations are thought to have been created during a period called cosmic inflation, a brief time when the universe expanded incredibly fast, smoothing out irregularities but also amplifying tiny quantum fluctuations into the seeds of galaxies. These tiny fluctuations existed on many scales, from subatomic to cosmic. As the universe expanded and cooled, matter was pulled into the denser regions by gravity. Gravity is the force that causes matter to clump together. But it doesn't act instantly everywhere. Instead, it pulls on nearby matter first, and over time, its influence spreads. This means that the largest structures in the universe took a very long time to form. Small clumps of matter collapsed into stars and star clusters. These then grouped into galaxies. Galaxies themselves grouped into clusters and superclusters, creating a vast cosmic web of matter stretching across billions of light years. When a large region of space becomes dense enough, it collapses under its own gravity. This collapse leads to the formation of stars and galaxies. The first structures to collapse were molecular clouds, huge clouds of gas and dust, mixed with dark matter. These clouds are the birthplaces of stars. Depending on their initial density, these clouds could take anywhere from 50 million to 250 million years to collapse and form stars. Denser clouds collapsed faster, while less dense ones took longer. As stars formed inside these clouds, they began to emit radiation and powerful winds. These effects made the environment very complex and dynamic. Over time, many stars formed in these early clouds, merging into the first galaxies. Some of these galaxies formed just 320 million years after the Big Bang, which is incredibly early in cosmic terms. JWST is expected to find even older galaxies and proto-galaxies, pushing our understanding further back in time. Inside individual galaxies, stars live and die, sometimes exploding as supernovae and spreading heavy elements. But these processes don't largely affect how galaxy clusters form on a cosmic scale. The growth of galaxy clusters depends mostly on the expansion of the universe, the initial density fluctuations, and how matter interacts over large distances. Before JWST, astronomers used a method called redshift to study distant galaxies. Redshift occurs because light from objects moving away from us stretches to longer, redder wavelengths. This effect is similar to how a siren changes pitch as an ambulance drives by, known as the Doppler effect. By measuring how much a galaxy's light is shifted, scientists can tell how fast it is moving away and how far it is. This is expressed using a parameter called z, where a larger z means a galaxy is farther away and older. By collecting data on many galaxies and their redshifts, astronomers can map the structure of the universe and understand its expansion and history. JWST's discovery of a proto-galaxy cluster is significant because it shows us how galaxies began to group and interact early in the universe's history. Galaxies within these clusters move very fast, sometimes at speeds of hundreds or thousands of kilometers per second relative to each other. When gas clouds in these clusters collide, they release enormous amounts of energy, often observed as X-rays by telescopes. These observations open new windows into the universe's early days and the forces shaping its evolution. As JWST continues to gather data, we expect to learn even more about the universe's mysterious beginnings and its vast, complex structure. Thank you for watching. Please subscribe to our channel and thanks for watching.